Great. Okay, so today we're talking about telescopes and binoculars. But first, I want to kind of just do a little review of what we talked about last class. So if you missed it, or it's been a while since you looked at the material that we talked about, we were looking at the solar system and what lies in it. So we looked at that the sun is a star, that there are 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then there's also 5 dwarf planets that we at least know of: Ceres, Pluto, Eris, Makemake, and Haumea. And I actually just found out today that Makemake and Haumea are actually named after goddesses of fertility from some, I guess, I can't remember how you would say the area, but the Pacific Islander cultures. They're from 2 different Pacific Islander regions, but they were named after that. So I believe Haumea is from Hawaii, and then Makemake is from the Papui, but really beautiful names. We also talked about how I think we talked about how there's the asteroid belt and the Kuiper belt and the Oort cloud, and they're at kind of different locations on Earth, well, not Earth, in the solar system, and they kind of tell us what lives over there. And so we know where the asteroids kind of inhabit. Meteors and asteroids sometimes are together, and then comets. And so that was really what we talked about. And I was wondering if we can take maybe 2 to 5 minutes, and if anybody has any questions or comments about the class that we had last week, or any questions about the assignment that you had to do, I will happily answer them now, just so that you don't have to sit and wait.
So just a reminder that if you want to ask some of those questions, you can do so in the chat on Facebook, and just make sure you include your first name and your location.
Give it a minute, and if we don't have any questions, then I will move on.
I think maybe we can keep going. People will think of their questions as we go through class today.
Sounds good. So today we are going to answer kind of a big question. So for each class that we're going to have a big question, or the main question that we're going to think about and answer during class. And then hopefully you'll be able to think more about it for the next week. And so this week's big question is, how do we view space? We can look at the sky outside and say, well, if it's clear, unlike today, if it's clear and we see stars, we know that they are these balls of light, and you know, we've been able to study them, but how did we study them, and how do we know so much about them? Because with just our eyes, we can only see so much. We're lucky that we have a moon for our planet, because that allows us to see with pretty decent detail what the moon does look like. But how do we see closer? How do we see stars and know what's in them? What are they made of? What are they doing? And so in order to actually see, you know, parts of space, or the other side of our solar system, we look through telescopes, or we can use binoculars. So these 2 ways allow us to be able to look out into space and to be able to make observations. But they aren't just these 2 ways, because they are actually very complex. So with telescopes, and do note this is not an exhaustive list or a complete list, And these are just the broad names of these types of telescopes. There's even more. So we'll only be focusing on 3, but some of the main ones that we have are refracting, reflecting, adaptive optical telescopes, atmospheric Cherenkov telescopes, infrared, radio, submillimeter, ultraviolet, and X-ray. Now, the main ones that you'll probably ever hear about are refracting, reflecting, and adaptive optics. And I have put it kind of at a different section of the class, but one thing you'll want to know is that we typically see refracting, reflecting, and adaptive optics here on Earth. And then we see more of infrared, radio, submillimeter, ultraviolet, and X-ray in space. And I'll explain a little bit more later about that. The picture you're seeing here is just a couple of the telescopes that are actually down in Mauna Kea, Hawaii, on Oahu. I actually applied to go to school here and work at these telescopes, but that's another story. So there's actually a group of different owned telescopes down on the island of Oahu, and they have different projects that they're working on, different things that they're researching, and they're not all the same type of telescope, and they're owned by different countries, different research organizations, but they all work together, and they're all on top of this. They're actually right on the mouth of a volcano. And you can actually see, if you go to Google Earth and you look up the Mauna Kea volcano, you'll actually see the different telescopes on the rim of the volcano, and it's really cool. You're like, whoa, that's so crazy that you guys are on top of a volcano, even though it hasn't been active. There is actually a very good reason for these types of situations with telescopes, but we'll get to that in a minute. So first, we're going to be looking at refractive. So without going too into detail about the physics of it, because it is very high level math, and this is a college course, and I had to take it. What happens is that there is light that comes in. Let me see if I can, where is my thing? Annotate, draw, great. Okay, so there it is. Okay, so over here is where light comes through the telescope, and it comes in, I don't even know where my thing is. So it comes in from here and here, but also comes in with all these like black lines. And this is just showing you where the light is coming in, and it hits a lens, which is this right here. And this lens is refracting or bending the light. It's why it's called a refracting telescope. So the light is coming in, it's being bent, and as the lines move towards the little green arrow, number 5, the light is being focused. And so as it's getting focused, it's actually being bent again through another lens, and it makes the eye see a clearer image, and it's going to be bigger, clearer, and magnified. So it's going to be bigger. And the image is virtual, which means that it's been flipped and it's on the other side of the lens. So it's not actually on the same side as the eye. And that can tell us kind of about what's going on with the light. Let me see if I can. I don't know where it is. Okay, there it is. Clear all drawings. Okay, right. So with this light being bent, it can look at things such as planets, moons, typically stars. Actually, one of the first refracting telescopes that we knew of was Galileo's telescope. This was the first telescope that, well, it wasn't the first telescope that was used, but it was the first one that actually like worked well. And it's actually what Galileo used to study Jupiter and look at its 4 of its moons, the Galilean moons that we know of, Io, Europa, Ganymede, and Callisto. And it was very popular for a very long time. And you can actually buy a refracting telescope. They're pretty popular. And definitely a good quality telescope. Yeah. Thank you. Great. Sorry, I'm trying to get out, guys. There we go. Next we have the reflecting telescope, and this takes the light from a star or any body that's giving off light, and it takes it through a different hole in the telescope. And so where the red is on the top part of the telescope, that is where the eye would see. And then where the green and purple are first coming in, that is where the light is coming through. So essentially, okay, don't judge me for using a shoe. So if this is a telescope and it's looking like this, so the light is coming in this way, and there's an eyepiece here. Essentially, to see what I'm looking at, I would look like this into the eyepiece. That's part of the telescope. It's called the eyepiece. It's where you look in, and it would look into that secondary mirror, and that's where the light is being reflected onto, so that it can hit the eye. So the light that's coming in through the opening that is looking at the stars, it comes in and hits a primary mirror, and that is that curved mirror, and that is called concave. I always mix up concave and convex. That is one thing I struggled with in optics, but I believe this is a concave mirror. It's a primary mirror, and then it gets focused on the edges of the mirror, so like this, and then they get bent towards a focal point, which is the gray X. And because there's a mirror in the way, they actually hit on the secondary mirror and hit the eye. And so Newton used this method and made his own. And I just realized I completely forgot about this. When you use binoculars, they don't use reflecting, they use refracting, which is really cool. Really cool. Drew, if someone's commenting, or if you're commenting in the chat, I can't actually view it because my mouse is like disappearing. No, great. Okay. Yeah. So we talked about refracting and reflecting, and we get those names because of how the light is being used in the telescope. So when it's a refracting telescope, it's because the light is being refracted or bent to the eye. And then we call it a reflecting telescope because the light is being reflected off of mirrors to hit the eye. So these were telescopes for the longest time that were the only kind of telescope used. And they've been developed and used primarily. Reflecting tends to be more popular because you can actually adjust problems that are being impacted by things such as the atmosphere, or like if something is shaking, or trying to focus that tends to be more popular. But there was a problem when we were looking at space. Things weren't very clear. It was very hard to actually see certain things because the atmosphere is getting in the way. So one thing that the atmosphere does, the atmosphere is like a big refracting telescope, except the problem is it's not magnifying anything, it's making things blurry, because as light is coming through the clouds are creating this sort of thing called interference, where the light is hitting particles of water and gas, and they're bouncing off, and they're not going where they were originally supposed to be going. So say there was light that was trying to go hit my hand down here, and this is the surface of Earth, and there's light that's coming down this way, but instead it came and hit my glasses, and so it went that way instead of hitting down. So I can sort of see the light because some of it is still going down this way, but not all of it, because some of it is going this way. And so that creates things to look very blurry or hazy. If you've ever been on the road on a hot day and you looked out and it looked like there was water all over the road, and you're like, that can't be, it's so hot. Well, that's because the light is getting bent by heat or gas. And so it's actually making it look weird. And so that was actually happening with these telescopes. And we did everything we could to make it look better. We put them on high mountains or volcanoes because on the tops of those places, there's actually less atmosphere between them. So that means there's less light being scattered or displaced or bouncing off each other, because there is less space between space and these places. And so it worked a little bit better, but not really. So how is it that we're able to get these nice pictures that everyone's like, oh my gosh, they're so pretty, or that looks so cool? Well, we use adaptive optics. And actually in this picture is a telescope that I worked with in undergrad when I was working to get my bachelor's of science in physics. And so this is a Meade LX200 ACF, or I think it's like anti-coma free. It's essentially it's coma free, which is saying that there's a certain grain on the lens that fixes light, and you don't need to really know about that, but it's really cool, and it means that I can look up at Jupiter and it really won't be as hazy on a hot summer day hot summer evening, and I can take better pictures with it. And you typically have this on the more scientific telescopes that are doing research around the world, or at universities or schools or something. So because they're really good, and they can without having to do your own editing, because that editing can take like days. I did my own editing for things where the telescope wasn't working, and it took like a week just to fix a picture. And so they do all of this fixing automatically when they work, right? And it's really awesome. So adaptive optics takes the properties of refracting and reflecting telescopes and mixes them together, and then applies another form of optics to fix it. And so adaptive optics has allowed us to be able to do high quality, fantastic edge-cutting research on things such as black holes or the sun. We also use adaptive optics with solar telescopes, and they've been really great because we can see qualities about the sun that we've never knew about, which is awesome. So I miss this telescope. Her name was Ace. I called it her because she and I were the only girls in the program for my research, and she was very dear to me. Yes. So I've been talking a lot about land-based telescopes, but I said something about space-based before. So, so what is so special about space-based? So we know about all these different satellites that are in space that we have sent up through different governments. So NASA has a ton, China has sent up a lot. The European Space Agency has sent up quite a number. And those always have some sort of camera on them. And so they usually have infrared meters that they have on there, gamma detection, which is done with the atmospheric Cherenkov telescopes, and ultraviolet, and I'm probably missing a few other, but regions of the light spectrum that we can't see with our eyes. And that will also be on your assignment afterwards, which I will talk about towards the end. But the space-based telescopes essentially allow us to do work that we aren't able to do on Earth because of things like the atmosphere, where adaptive optics doesn't always work the best. So it is pretty good, but it's not the best. And so working in space where there's no medium for disruption, it's the perfect place to conduct research. And you also have things that are spinning around Earth, facing all these different directions. And so you're able to essentially look in all these different places of space and say, oh, cool, this is something that I caught on this day, this time, at this year, and does this information match up with something that was also at this location at a different time? And things like the Hubble telescope, that had so many awesome data points that were taken in, and data points are it's information that we've taken in from things that we've looked at and said, okay, so this is what it's telling us about this star or that exoplanet. And it's very useful to have various different types of telescopes on a let's call it a Seattle. Seattle's a town. I mean, it's a city. But satellites are very useful because it can combine different images with different sources. And so when we see pictures like galaxies where they have all these different colors and they're very vibrant, those actually aren't what they look like to the eye. That's from using the combinations of different types of telescopes, because they have various shades across the light spectrum. And so that's very, very useful for us. So between using space-based and Earth-based telescopes, we're able to see a whole wide range of what stars can look like. We can even hear what they sound like using radio waves. And I'll attach that on your assignment where you can actually listen on YouTube. NASA created a playlist with what the universe sounds like, based off of the radio and gamma rays that they collected. And it's very cool. It's kind of creepy just because it's kind of like a shimmering sound, and it's very cool. I think you guys would like that. So that was telescopes. And so next we're going to talk about binoculars. And binoculars are a form of refracting light. So they go in through the eyepiece, the two ends. So it's two telescopes that have been put together to create one field of vision. So it's just like how we have two eyes, they're just like telescopes or binoculars. And if you close one eye, you can see kind of this one section of what's in front of you. And if you close your other eye, if you switch it, you actually see even more on this side, but you can't see this part. And so when you open both eyes, you have the entire view that you can see. And a pair of binoculars is just the same way. And so it's taking the form of a refracting telescope, puts them into a smaller portion, and then puts them together so that it's like you're looking through your own personal telescope, but you don't have to pay a lot of money for that, and it's useful for looking at things that aren't just for space. And so I thought, instead of just having pictures of them on a PowerPoint, I'd show you a really cool website that I found that talks a little bit about them and has pictures of them. So that would be good. So let's exit this, and I'm gonna stop this share. I'm gonna go to something else. Where is it? Oh, here it is. So the types of binoculars that we're talking about here are, like I said, they're all refracting telescopes. And so when we're talking about binoculars, it just talks about the way that the binoculars work. And so there's a roof prism binocular, which is very similar to poro prism. That's what this here is. It's a roof prism. And essentially, it collects light that is bouncing off from different directions. So light doesn't just flow in one way. So the light that you're seeing of me going into the camera, it's not all just going straight this way. It's actually bouncing off my face, maybe bouncing off the laptop, bouncing back to my face, then to the camera. Or it's, there's a lot of light coming and hitting my shoulder, so it actually looks very, very white. But there's not a lot of light hitting this side of my face, so it looks a little darker. And so light's coming in different ways. So all that light enters this binoculars, and then it bounces around in those binoculars until it hits the eyepieces that are on the end. So the light isn't necessarily traveling in exactly the same way as a refracting telescope, because there's only a couple of ways that it goes through, but this is, it's a little bit more complex, but it's essentially the same thing. And so this, this model compared to the poro prism, which we will see, is that it has a higher magnification. So if you wear glasses, you know that your glasses have a certain power to them, and that just tells you how strong your prescription is, whether you need more of a positive to see closer to you, or a negative to see further. So my glasses, which are basically refracting telescopes, but they're only going through one lens, not two, they're negative, and the greater the negative power, it means the essentially the further away I can't see. And so that's what binoculars are like. So the poro prism, the roof prism are typically used by hunters and birders because they can see pretty far. The poro prism is, so the telescopes are a little bit further away, and then it triangulates towards the eyepiece. And so they send waves of light in a specific way that can make the shape look a little bit I don't know how to explain that their shape and strength are heavier. It's just that they, I guess they look, they're not as clear as the roof prism, but they have a better chance. You can see further with them, and you can see more because they are further away from each other. Night vision, so cool. The fact that we discovered this just blows my mind. So guys, it's so cool. So night vision binoculars actually take light in through them. They filter the light through a lens. Well, not a lens. They filter light through a filtered lens, which basically is saying that there is a tint on the lens, and because of that tint, it actually can either absorb all of that color or it can emit only that color. So if it absorbs, it means that if you are looking at something that is green and it's absorbing all these colors, if it's only absorbing green, it's going to appear every color mixed together except green. So I guess that'd be like a brown. But when it's reflecting green, so yeah, if it's emitting green, which also just basically means that it's reflecting it out, basically every color is getting absorbed, which is what we see with color. Every color of the rainbow is hitting this material, but it's only appearing green because it's giving off the color green. And so, yeah, this is actually every color but green because it's absorbing all that color. Light is so cool, guys. So with these devices, it translates into a green hue for optimal eye absorption and darkness. So essentially, everything around you is going to appear green. Yeah, maybe switch on. Essentially, so everything's going to appear green, but it's not going to be very magnified. So it's going to look at everything around you. It may be a little bit, may look a little pushed away because of the magnitude. The way that it works is that it doesn't look very close up. So it can be, it can look very similar to what things will look like around you without using regular telescopes. And the image will be kind of blurred because the image won't be blurred because it doesn't have a higher magnification. So this is actually really good for when you're going out in wildlife at night. You also probably see it if you watch shows like Searching for Bigfoot or Ghost Hunters. They use cameras that use night vision because you can see around at night and you won't trip over something because it's not blurred to you. Or people can use it at night for camping because it's really good. So cool. Oh, by the way, it does all of this electronically. So it just like has a computer that does this and it just automatically sends it to your eye, which is really cool because these other two don't do that. It's just using optics to get one field of view or one entire view into your brain and you make you understand it. So this does all of that and more. Marine binoculars are kind of, well, not kind of cool, they are pretty cool. They don't have a very high magnification strength or power, but they do have a really decent lens size, which means that they take in more light. And then because of the distance or that the fact that you can change how close they get to each other means that you can adjust on your own how much of what you're looking at you can actually see. So because the magnification is pretty small or average, you won't feel like you're constantly shaking when you're at sea. And so you'll be able to see ships, dolphins, marine birds, cool waves. It's also really great for watching when whales either like backflip into the air or their tails are going up. And so you can really see with detail. not like extreme detail that you would kind of want to see, but it gives you enough to be able to say, wow, that is really cool. And typically these binoculars are made to be weatherproof, which isn't an aspect of optics. It's just marketing and making it so that they don't get destroyed in water, which is smart because they are being used at sea. And then one thing you will usually see, and you can actually find this in our planetarium, well, not in our planetarium, in our shop at the at the museum. Oh, words are hard today. These are astronomy binoculars. And so these have a very wide lens length. We call that a diameter. So that is, if you have a circle, it's the amount of space directly in between cutting a circle in half. And that's the complete distance. The radius is half of that. And so when we're looking at astronomy binoculars, they are really wide because they want to take in as much light as possible, because at night, you don't have a lot of light, and so you want to receive as much light as you can to be able to see all the stars, planets, moons, shooting stars as possible. And so it has a very strong magnification because you're also looking very far. So as it says here, a 10 by 50 binocular will actually make the moon and planets look very sharp. You should be able to see satellites, the space station, comets, and comets don't move that fast, so you'll be able to see them very well for a very long time. And then meteors. So when those are falling or streaking, you can see those and look really cool. Because already seeing a shooting star, which is just a meteor falling down or some sort of space debris, that already looks really cool. But imagine being able to see like the actual body of the streak and be able to say, oh my God, I saw that. That is so cool. And so you can actually usually hold them with your hands, or sometimes they have tripods, which are 3 legs that will hold the binoculars for you. You also typically will see telescopes with that. They will always have a mount, and there's different types of mounts. They're not really that important. I mean, they're important, but they're not like something that you need. So yeah, a tripod can help because higher magnification has a shaky image, which basically means that you already are shaking because your hands can't really stay still, and the earth is moving at about 1,000 miles per hour. And so it's going to appear shaky. So if you have a tripod, it'll make it easier to view. And then opera glasses. These are not that common. You'll always see them in period movies or movies that take place, maybe 50 to 200 years ago. And these are very popular, where if you're going to an opera show or a play or something, or Broadway, they are fashion accessories, but they also allow you to see the stage if you're sitting far away. Typically, it was used by members of society that were sitting on the wings of the theater, so on the sides, and so you can't always see things very clearly. So essentially, what they're doing is they're held by one piece, and they look through them like this. Well, not like that, but imagine that this is held down, and so they're looking like this, and they hold it to their eyes, and they can see decently close enough that they can see what's going on the stage in focus. So they're not that connected, but I mean, they're not that magnified, so they're not super clear, but they're easy and portable to use. And so those are opera glasses. And so with the activity that you're going to be having after today, and feel free to do this during the week, you're going to use a website that I'm going to send you, and You're just going to look at the night sky, or if you have a telescope, I would love for you to use that, learn how to use it, or ask your parent to learn how to use it with you. That's such a great thing. My mom and I used to do that. We would use my telescope and use that together. I have a refracting telescope, and man, I wish I brought it with me. Yeah, that'd be really great if you had one. If you don't, no worries. The website I'm going to send you is not going to have any telescopes, but it'll allow you to view the stars. And if you can find a pair of binoculars, or you can try to make some yourself. Actually, if you close your hands and you make them really close, you can actually sort of form a telescope, or try looking at something that has water on the end. Water actually acts as a lens and can bend the light. And then you're also going to have some vocabulary that I'll give you the definitions and see if you can use them. Work maybe a story, or maybe write some sentences about them, and something that you learned. And I would love to know if you were going to look at a star yourself, what kind of telescope are you going to use and why? So I'll write all of that out for you, and you won't have to remember that on your own. But yes, that is telescopes and binoculars. So if you have any questions right now, I'll be very happy to answer them. Some comments. Love to hear it.
So yeah, we'll give people a few minutes. So if you're on Facebook Live right now, watching along with Hannah, now's your chance to put your questions in that chat screen, and we will ask them of Hannah. So we'll just give everybody a few seconds. And if we don't have questions today, I just want to remind everybody that you'll be able to find Hannah's worksheet. And remember, for your badge, these worksheets are a required part of the badge. So you'll find our class from last week on the Facebook page for the Girl Scouts of the Green and White Mountains, as well as on the Fairbanks Museum page, which is fairbanksmuseum.org. As along with these worksheets. So there were worksheets for last week, and we'll be posting the new ones as well for this week. So I don't think we have any questions today, it looks like, but I'm sure next week we'll have tons and tons of questions. So I hope you guys stay tuned. This is, as I said earlier, this is our second class of 4 for the Space Science Adventurer badge for Brownies. And we were really thankful to have you all here today. Of course, I want to extend a huge warm thanks to Hannah for teaching. And if you're a junior and you might be stumbling onto the Facebook page right now where this is broadcast, don't worry, we'll be back at 4 o'clock to teach the Space Science Investigator badge for juniors. So thanks, everybody. All right, have a good day.